God, that's bright. I can't see. Good afternoon. Thank you for attending our presentation around our advancements in formatting of thermoplastic composites to improve the bias-ply ratios. I'm here with Jim Powers. Jim is our Business Development Director for Thermoplastics on a global basis. I'm Ashley GRAEBER. I head up our Sales and Business Development team in North America. Together, we're representing Web Industries. Web is a global leader in composites formatting for aerospace applications. We're best known for pioneering precision slit tape for automated fiber placement applications on the 787, 777X, and A350. Okay, how do I advance the slide? How do I advance the slide? Okay, thank you. Okay, thank you. So our mission around this presentation today is to present thermoplastic composite formatting, as I just mentioned. Our overall mission is to position thermoplastics for next generation aircraft structures. So moving from thermosets to thermoplastics, higher production rates, get rid of freezers and autoclaves, so a much more position to enable high rate production. In collaboration with our material manufacturing partners and the equipment manufacturers, we're working to enable commercial scale production, as I just mentioned, optimize the material formatting to support a broad range of manufacturing processes, and as the title of our presentation, improve the overall bias-ply ratio. So Jim is going to walk us through those different formats and the manufacturing processes that they support, and we'll hopefully have a few minutes at the end to answer any questions.
Thank you, Ashley. I'd like to start off with a little bit of history on what we're doing on thermoplastic format development. With aerospace moving more and more towards thermoplastic materials, with our history in formatting thermoset products, we want to utilize that experience and move forward in a lot of the formatting understanding and processes and fabrication techniques used in thermoplastics. And from that, we want to be able to utilize the existing materials that are out there. The list is relatively short, but the materials are made by a few manufacturers, and they're really the high temperature materials that we focus on, the PEEK, the PEC, PEK, and PPS. There's some PEI that we may mess around with, but realistically, these are the materials that we're seeing being used in aerospace. They're approved. There are specifications written for them, and there's a lot of development work going on. What we want to be able to do is customize and look at the different slit tape formats that are being used. With thermoplastics, there's many fabrication technologies that can be used. There's more than one way to make a part. Okay, so it has to be optimized at the process level for fabrication, and to do that, it has to start from the material supplier and work all the way through the supply chain in order to optimize that process. And that's an ongoing development side. We want to be there to support it for all kinds of technologies. From that, we also have to customize the formats, not only to meet that, but we have to be able to splice those materials. We have to be able to create very large format rolls, large material, because you're not using the freezers. It's environmentally friendly material, and it can stay on a machine overnight, and you don't have to worry about the thermoplastic material out time or anything like that for processing. And then going forward, we want to talk a little bit about our advanced processing and innovation, and it's a bias-ply format that we've developed, that we've introduced here at the show, and it's in our booth, so we can talk about that in a little bit. And then also going forward, we understand what's happening in the aerospace world for thermoplastics, because as associate member of TPRC, we get some good visibility to what's happening, especially here in Europe, where green technology is very important in thermoplastics and the advancements of high volume output and the reasons behind both the thermoplastics and recyclability. So let me start off with a little bit of history. We're the technology leader when it comes to formatting materials. We have a 50-year history with the company for formatting a whole bunch of materials. And what we took from that is we were able to develop a process for composite materials, starting with thermal sets. So we have a history of spec writing and development of processes on the thermoset side for large commercial aircraft, launch vehicles. There's some other small programs that we're working on, but that's been the driver. And over the last 20 years, we've learned a lot from that technology and the process. And so we're taking that and turning it into a thermoplastic process optimization. So lessons learned over the last 20 years has allowed us to look at all the different fabrication methods that are being potentially utilized for the advancement of what I'll call fast aircraft manufacturing, fast commercial, VTOL, anything that's going to be looking at high volume, monthly, big aircraft and along those lines for scale. We look at optimizing our processes, AFP, ATL. How do we format the materials for thermoplastics? What's the best way to go? Like I said, in thermosets, we're always looking at like 8 kg spool, maybe 10 kg spools, but for thermoplastics, we're not limited to the size of the spools because we're not worried about the out time of the material. So that's not a limiting factor for us. So we can actually create some very large product that can be used and processed through the AFP or ATL. We also look at braiding is a technology that's coming out, and also additive manufacturing, which I call basically micro AFP because it gets down to very small slit widths of 1 millimeter. And then I mentioned the bias-ply a few minutes ago for use in continuous compression molding and also some thermoforming. I'll touch base on that. And then we develop, in order to make all this work, the manufacturers create their master rolls and bring it in. In order to create these big spools that are used in the fabrication processes, we have to develop splicing technology that's fast, accurate, and meets all the requirements and specifications for the fabrication process. And then normally we talk about slit widths. We can actually go very wide, but for the technology we're talking about today, we're looking at 1 millimeter to 2 inches realistically for a lot of the thermoplastic fabrication processes that are out there or soon to be developed. So I'm gonna talk about the bias-ply real quick because that's kind of where the bias-to-fly ratio comes into play. There's processes out there with specifically a continuous compression molding as well as thermoforming that needs isotropic layups. And in order to get there, right now the process to create these plus or minus 90-degree rolls or plies is a hand process. So they're butt welding them together, and it's a labor-intensive process. Plus, when you do that, it's not a custom size, so they take this and try and run it through a CCM machine, and you end up with a lot of waste. So we developed a process that allows us to create a very large-scale roll through an automated process that can be up to 50 inches wide, that manufactures the 45s, plus or minus 45s, or 90-degree rolls, that is then automated. You can see in the pictures, I think this has got a, you can see in the pictures, you can see the roll that comes off, and also custom slit widths that can accompany that for CCM. And what this does is we have, first of all, the bias-ply is made very rapidly with custom overlap of roughly 2 millimeters, and we control that alignment very, very tightly. We have 100% inspection on it, and then we capture that critical data for use at the end customer if they need it. And then what we're able to do to reduce the bias-to-fly ratio so that the cost of the parts is more attractive to the end user is we can create the individual rolls like you see in the middle picture here, where your first ply in a CCM can be 10 inches, your second one can be 10.1 inches, third one 10.3, so you get a very discrete finish and your waste is reduced to very little if none. And so that's the goal of this technology. And we can create these in 50 inches wide as well as 25 inches wide. The other way to do this is we can take the rolls, the bias-ply itself, and create blanks for thermoforming. So we can actually create the ply layups. It could be 10, 20 different plies laid up that can be used for consolidation, and then you can either cut out shapes for thermoforming or use the whole sheet for thermoforming. And it reduces a lot of the hand labor and in the content of making this type of material. We're also involved with, so additive manufacturing is an up-and-coming technology too for aerospace, because it uses they want to use the same materials as the AFP and ATL, right? Because these are already approved materials. There's specs for them. There's probably NCAMP certification for some of them, but it allows for the additive manufacturing developers to use homogeneous materials that already have approval. So it reduces potentially the requirements for part approval, helps on the design because allowables are there to design using these materials. And again, it's the same that we use for AFP and ATL. So what we're doing is we're scaling down. So we're able to make very narrow slit tape, 1 millimeter wide, with still holding a tolerance of plus or minus 5 thousandths on this tape. And then depending on the additive manufacturing equipment manufacturers, we then custom make the spools that fit those machines. And we're working with those companies in the short term for trial work, but then we can show scale. So we can actually, 1 millimeter, we can slit a lot of 1 millimeter at one time and create multiple packages for the end user. So we have the custom packaging, the spools, cassettes, and we're able to deliver. The idea is to get the materials in without defects. If they come in with defects and we have to remove them, then we would look at splicing. Some additive manufacturers can accept splicing, which in this case would be thermal, or not. But in order to really make additive manufacturing work right, and you get and just like in AFP and ATL, you need to have the flyaway splices. So we're working with the manufacturers to say what's the best way to splice this material together, so we can again make these very long rolls or spools that can be used in this process, which is very advantageous because they can make big spools that can sit in the equipment for an extended period of time. We also have what we call a chop flake, and this is also can be used for raw material, for virgin material, for parts, for compression molding, or we can capture it for recycling. Let me explain that. So we can take the big master rolls that come in and we can slit it down to a half by half inch width, half inch chop. We can slit it to 1/16 and chop it to half, or we can take trim off your production spooling for ATL and capture that and reclaim it, and also process it for recyclability or for other things besides AFP, ATL, or compression molding. So we're able to capture probably close to 99% of the material through this process. Okay, so when we do run 1/4 inch for AFP and slit it, then on the edge trim we can capture that and hold that back for other types of processes using virgin material. The chop, the half by half and the 1/16 by half is to a spec that can be used in compression molding that's been approved for use in aerospace. We can then custom package that for the right use for compression molding, so we can bag and tag it. We have complete traceability on all these materials, and then we can deliver those packages to the end user for specific applications in the compression molding. So in summary, this is pretty good because why are we doing this? Because the thermoplastic world is positioning themselves across the globe really that's the next generation of composite materials because of the high volume requirements, production, the welding capability of the material, the damage tolerance, chemical resistance, all the assets of this material, of the thermoplastic materials for next gen aircraft. It's a high build rate. It's, they're looking at some, we hear numbers like 60 a month of just one airplane. Well, there's 4, 5, 6 airplanes that are being looked at to build at that type of scale. You can't do that with an autoclave. So the idea is how fast can you build? So we're supporting that growth in the aerospace world to handle those higher volumes. To we're scalable. We're already there. We can scale more to support this. Again, to optimize the format. We work with the end user. We work with the fabricator. We work with the machine manufacturer to optimize the process, to really lean out the supply chain and have a very linear situation where we're all talking to each other to really get to the end goal of putting these materials on aircraft and reducing the overall costs. So that what we're looking to do is totally improve the buy-to-fly ratio through innovation. So we do that through the collaboration, as I just mentioned, next generation processes. We're continually looking to innovate. We have a broad range. So what we have now is not necessarily what we're going to have next month or next year. We're continually innovating our processes to support the innovation out there in the industry for next-gen processes. That includes longer spools, bias-ply, chop, any technology that's out there. We want to be able to support to put these materials into the system in order for thermoplastics to be successful long-term. So at this time, I guess if we have any questions, comments, we can address those. Thoughts? No? Sorry? Sorry? Yeah, so if there's no questions, we're booth here in Hall 5 at G21. And we have all these examples in our booth, and we have our bias-ply, which is a 50-inch roll. It's the first of its kind that we'd be happy to talk to you and show you. Okay? Thank you.
Everybody comes from somewhere else to LA, and that's where the funk comes. We just bring it all in from Cincinnati, Chicago, everywhere. So tonight, this part of the journey